Welcome back. This is the second of the additional electrophilic reaction that I want to walk you through it. Now, if you remember in the previous video, I pointed out two important aspects about sulfuric acid, which is this right here. Okay. Now, sulfuric acid can be a dehydrating agent, as I said. If it is a dehydrating agent, means it can remove water, right? It can remove water. Or sulfuric acid is also a rich source of proton, which is H+, which was used in the previous case. So if you're starting with a double bond, okay, and you add H2SO4, the proton-rich property comes out, so you end up making an alcohol, okay? You add a OH group to, essentially one of your double bond is gone, and you add a OH. Whereas if you're starting with an OH plus a sulfuric acid, then the dehydrating agent property of sulfuric acid comes into picture, and you make a double bond. Now, there are two clues on that you will make a double bond. One of them is, first, you're starting with an OH here, right? Second, you're starting with heat. Now, whenever you have heat and sulfuric acid together and you have a OH, that's a pretty good indication that you're going to be eliminating water molecule. Now, let me write the product first, okay, which is basically you remove the OH and the hydrogen from one of the beta positions. So technically, you can have a double bond here, or I'll show you a double bond here. These are the two products possible. Now let's look at the mechanism here, okay? So here's your starting material, okay, plus your H2SO4. Now we will see another compound, which is a slightly modified version of this compound, where we are going to see the hydride shift that we learned when we learned the material for exam 1. Okay, now whenever you add sulfuric acid, now sulfuric acid is a proton-rich compound, okay, and so it's initially going to give away proton before it takes away the water molecule. So what is going to happen is I'm going to rewrite this as H and HSO4. Okay, I just rewrote this H2SO4 as H and H2SO4. Now what that's going to react is the lone pair on the oxygen is going to react with the hydrogen and grabs it, and in the process cleaves this HSO4. So what is going to happen now here is, so let's get our red back. Okay. So we have essentially abstracted a proton from the sulfuric acid and then made this. This is an intermediate, okay? This is an intermediate. So typically we put intermediates in a bracket, all right, plus HSO4 minus. Okay, now let me get a different color, maybe purple, okay, something dark. All right, now what's going to happen here is the OH2 is going to come off because it's unstable. Whenever you have a molecule with OH2 plus, the OH2 plus is highly unstable and it doesn't want to be in that form for too long. So what's going to happen here is you're going to be ending up with the plus charge directly on the carbon plus water. Okay. Now, if you remember from our exam 1 material, I'm going to do something which might hopefully bring your memory back. Now, this is the carbon that was containing the leaving group, right? So that was the alpha, right? So this must have been the beta, and so is this. Now, each of this carbon is a bend, so they all contain two hydrogens, right? Now, you could choose to remove one of these hydrogen, and then the bond comes back. I'm going to again switch colors, so it's a multitude of colors to really understand this process. Okay, what's going to happen here is, remember that HSO4 minus we cleaved? It's going to come and grab this hydrogen, and in the process this bond is going to come here, and then when a bond comes in, it brings in a negative charge which neutralizes the positive charge. So it's going to give you this, which is one of the products, right? If this were the case, if you remove this beta hydrogen, I mean, you have the option to remove one of these two. They're identical. It doesn't matter which one. But if you chose to remove from this beta carbon, then this would be the product. All right, I am going to switch color again, get a different color this time, red perhaps. I have already too many red, so let's get a different color, maybe orange. Okay, so let's say I chose to remove this hydrogen. Okay, in that case, this bond comes back here. Okay, it can only go towards the positive charge. Okay, it cannot go to this carbon or this carbon or this carbon. Okay, because it has to neutralize that positive charge. And if that's the case, I'm going to write R here. You will end up with this as your compound. Both are equally possible. There is no one is not better than the other, or one is not more favorable than the other, because there are no substituents hindering the way. You can think that there's a 50-50 chance that they're both possible. Okay, they're equally possible. One does not weigh the other. Okay, now I'm going to stop this video here. You know, all I want you to take away from this is there's a difference, which is this. I'm going to box that so you can see it. In the previous case, we looked at the double bond with sulfuric acid, and you see there was no heat. So whenever you have a double bond on a sulfuric acid, you add a OH. Okay, now if you have a OH and H2SO4, then that's called dehydration, and you're going to get rid of water. You see, you have got rid of water here in the process. So that's how we got to get the double bond out of the molecule. Okay, so I'm going to stop this video here and bring the second. Now there is no need for a hydride shift here, because there is, I mean, you can't really do it. That's just the way it is. But I'm going to show you another compound where we can have multitude of products, and I'll show you how that works. All right, so stay tuned.